Hello, I'm Andrew Logan and I'm going to go over my paper which gives a proof of the Riemann hypothesis, or why the Riemann z function has only real zeros. I'm going to be using incomplete gamma series and power series to do this. You can find the paper itself at this website, or alternatively if you search for Riemann hypothesis Logan you should be able to find it. If you have any questions or comments then please do get in touch using this email address. Looking at the structure of the paper itself, it's in two main sections corresponding to the two different integration approaches to Riemann's original equation. The first giving a series of incomplete gamma functions and the second as a power series. We'll be looking at the characteristics of these two series and what happens when we vary the components of the series. Diving into the paper itself, both series start from Riemann's original equation from his 1857 paper, which we can see here. For the first series, incomplete gamma functions, what we'll do is we will look at some substitutions, setting t over 2 equals a plus bi, remembering that cos x can be written as a half e to the ix plus e to the minus ix, and with a variable substitution y equals m squared x. Working through those, then we results in two expressions with incomplete gamma functions, namely gamma to the 9 over 4 minus b plus ai m squared pi and gamma to the 9 over plus b minus ai m squared pi, expression 1, and similarly gamma to the 5 over 4 minus b plus ai m squared pi and gamma to the 5 over 4 plus b minus ai m squared pi, expression 2. Summing those two expressions will give the Riemann z function. Looking at the properties of incomplete gamma functions in more detail, and remembering that for all that follows we'll restrict the value of b from plus a half to minus a half. We can do that because Riemann proved in his original paper that there are no zeros of the Riemann z function, with t having imaginary parts outside the region of half I to minus half I, equivalent to restricting b in the above expressions. Firstly, for the gamma 9 over 4 minus or plus b plus or minus ai and gamma 5 over 4 minus or plus b plus or minus ai. These are all incomplete gamma functions with the real part of s positive and smaller than x if we consider the function in the form gamma sx. Nielsen proved that all zeros of that function for x greater than 0 lie in the half plane real part of s is greater than x. Now in these cases m squared pi is always greater than 5 over 4 plus or minus b, and 5 over 4 plus or minus b is always positive. Therefore each incomplete gamma function has no zeros. Also, with fixed b and varying a, as a increases the magnitude of the function decreases. We can see this if we look at the product representation of the factorial function for the complex number s as known to Euler. And remembering that s times gamma s is equal to the factorial function of s. Looking at it in more detail, gamma of s equals the limit as n tends to infinity of n factorial times n plus 1 to the power s over s, s plus 1, s plus 2, etc. If we consider s equals b plus ai with fixed b, then for any value of n, as a increases in magnitude, both real and imaginary components of the n plus 1 to the s term are oscillatory about 0, and the term has a constant magnitude, while the denominator increases in magnitude. So, in the limit, this leads to a function of decreasing magnitude and tending to 0. In addition, if we look at the series expansion of the upper incomplete gamma function from the DLMF website that we can see here, gamma of sx equals gamma s minus the components under the sum, it can be seen that for the fixed real part of s with the real part of s greater than 0 and increasing size of imaginary part of s and x equals m squared pi, the sum component decreases in magnitude and tends to 0 in the limit. Since the gamma function also decreases and tends to 0 at the same limit, then we know that the upper incomplete gamma function also decreases and tends to 0 at the same time. Looking at some of the other components of the two expressions, expression 1 and expression 2, half m squared pi to the minus quarter, positive real result, reducing in magnitude quite rapidly as m increases. Also, m squared pi b to the minus ai and m squared pi minus b to the plus ai, both of those result in constant magnitude results for fixed b and varying a, real results for a equals 0, complex results otherwise. When b equals 0, they are of identical magnitude, identical real parts, and complex parts reflected across the axis, non-zero for all ab, of course. Looking at all of those, at this point we conclude that each of the expressions below, these four expressions here, which if we sum them add up to the Riemann z function, each of those expressions tends to zero in the limit, which means that the Riemann z function tends to zero in the limit. Next, if we look at the relative magnitudes of the incomplete gamma functions as b is varied, starting with the definition of the upper incomplete gamma function with this integral, rearranging the integral into this form, we can see that for any fixed value of a, and t being greater than or equal to m squared pi, and therefore log t always greater than 1, the magnitude of the integral will increase as positive b increases, since the magnitude of the real part of the integrand increases by e to the b log t. Similarly, the behaviour, the increase in magnitude, can be seen as a consequence of the known property of the upper incomplete gamma function, gamma s plus 1x equals s gamma s of x plus x to the s e to the minus x. Here we have two illustrations of the upper incomplete gamma functions for gamma 9 over 4 plus or minus b plus or minus ai, and gamma 5 over 4 minus or plus b plus or minus ai, where we can see the magnitudes decreasing as b increases. So you can see here the magnitude 0.6, 0.4, 0.2, and here 0.15, 0.1, 0.005, illustrating what we've shown above. Now, taking the expressions to the next stage, remembering this property of the incomplete gamma functions, gamma s plus 1x equals s gamma s of x plus x to the s e to the minus x, substituting those into expression 1 and 2, then we work through those and we end up with expressions 3 and 4, where we have only two upper incomplete gamma functions, gamma 5 over 4 minus b plus ai and gamma 5 over 4 plus b minus ai. These gamma functions are multiplied by linear variations on the variable s, as you can see here, 5/8 minus b over 2 plus a over 2i minus 3/4, 5/8 plus b over 2 minus a over 2i minus 3/4, and each plus a real amount, a real constant. Taking that one stage further and using the continued fraction representation of the incomplete gamma function from Abramowitz and Stegun, so gamma sx equals e to the minus x, x to the s continued fraction representation, substituting that into expressions 3 and 4, then we end up with expressions 5 and 6. Very interesting. Continued fraction representation times a real value, but also multiplied by a linear variation on s and adding a real constant. Similarly for expression 5 and expression 6. If we investigate the properties of the continued fraction components further, we find some more interesting things. So firstly, rearranging the definition, so continued fraction equals upper incomplete gamma function divided by e to the minus x, x to the s. Firstly, we can see immediately that the continued fraction expression will have a magnitude less than 1 and decreasing for increasing x. Secondly, remembering that for complex s and fixed real part of s and real x, the incomplete gamma function decreases in magnitude for increasing imaginary part of s and has oscillatory real and imaginary parts generated by real terms to the power s plus integers. In the series expansion from DLMF, we would expect the continued fraction function to have real and imaginary components that do not oscillate about 0. They may vary slightly, but they won't oscillate about zero, and decreasing magnitude, since the definition shows the continued fraction is equal to the incomplete gamma function divided by a term of constant magnitude and an oscillatory component in x to the power s. Note, this means that individually the real and imaginary components of the continued fraction part will have no zeros. Also note, for the fixed real part, the continued fraction values for gamma 5 over 4 plus b minus ai m squared pi and gamma 5 over 4 minus b plus ai m squared pi will both have positive real components, but the continued fraction values for 5 over 4 minus b plus I will have positive imaginary, and the continued fraction values for gamma 5 over 4 plus b minus ai will have negative imaginary components. When b equals 0, the real components of each function will be identical, and the imaginary components of the functions will identically sum to 0. At the same time, considering the alternative series expansion of the upper incomplete gamma function from DLMF, which we see here, upper incomplete gamma function equals gamma function times 1 minus this term, and if we compare that with the continued fraction expansion of the gamma function, we can see that for fixed s and increasing x, again subject to real part of s greater than 1 and x equals m squared pi, the magnitude of the continued fraction term reduces as x increases, since the x to the power k terms in the series expansion increase in magnitude. Also, we note that when b does not equal 0, the magnitude of the continued fraction component of gamma 5 over 4 plus b minus ai will be greater than the magnitude of 5 over 4 plus or minus ai, and the magnitude of 5 over 4 minus b plus ai will be smaller than the magnitude of gamma 5 over 4 plus or minus ai. In addition, referring to the rearranged definition of the continued fraction component above, the reduction in magnitude for the continued fraction component of the gamma 5 over 4 minus b plus ai term will be greater than the increase in magnitude of the gamma 5 over 4 plus b minus ai term, but by a value of less than b over 2. Finally, we look at the derivative of the incomplete gamma function with respect to x, which is minus x to the s minus 1 e to the minus x, which means that for constant s and x equals m squared pi, as x increases, then the derivative with respect to x decreases in magnitude. This is, in fact, all of these points we observe in the figures below. We can see for m equals 1, m equals 2, and m equals 3. Taking that a stage further, we'll be looking at the other components of expressions 5 and 6. Firstly, the m squared pi e to the minus m squared pi components. Real, and as m increases, they decrease in magnitude very rapidly and consistently. Secondly, the linear variations on s, minus an eighth minus b over 2 plus a over 2i, and minus an eighth plus b over 2 minus a over 2i. We can see, as for fixed b and as a varies, increasing in magnitude almost linearly, as we can see in this expression here, see in this graph here. Now, considering the implications of varying a and varying b in the whole expressions, so considering continued fraction times minus an eighth minus b over 2 plus a over 2i plus a half from expression 5, and similarly from expression 6, if the components of the continued fraction component, especially imaginary, are large enough, then it is possible for the complete expressions to have a negative real part for large enough imaginary part of s. The real part would start positive for no imaginary, reduce in value to negative for some value of the imaginary part of s, then changing direction and tending to 0 in the limit from below. The decreasing nature of the incomplete gamma function above does not allow for an additional change of sign when multiplied by a linear term, as in this case. If the components are not large enough, then the real part of the expression stays positive. Note, as m squared pi increases, the continued fraction components reduce in size for constant s, as we noted above. The characteristics of similar sign real parts and opposite sign imaginary parts will continue, with the sum of the imaginary parts of expression 5 and expression 6 vanishing when b equals 0. We can see all of this in this. Wait a moment, here it comes. In this expression here, for varying b, we can see the various sizes of the expressions in these two illustrations. Looking in those in more detail, we can see here you've got the imaginary component b equals 0, b equals 0.25 and b equals 0.5, and the real components here as well, with b equals 5, b equals 0.25 and b equals 0 there. So you can see the variations there. Looking at that in more detail, we can see here as well the same thing, the variations as b increases, the changes in magnitude. Quite interesting. Going back to the paper, here we are. Focusing now on what happens when b equals 0. If we look at in detail at those characteristics, b equals 0, so there's only a real component. For m equals 1, the expression is negative above a certain value of a, tending to 0 in the limit below. Looking back again at this one, we can see here for the lines here, you can see coming down, coming up and staying below 0. We look at the green line there is more or less 0, but you see it stays below. This is what we see when m equals 1. M equals 2, we can see the real parts coming above 0, positive m equals 2, m equals 3, which is what we see here. M equals 1, negative expression above a certain value of a, tending to 0 in the limit from below, which is what you've just seen. So for m equals 1, the expression has 1, 0. For m equals 2, the expression is always positive and tending to 0 at the limit. That means for each m bigger than 2, greater than 2, the expression will be positive and tending to 0. As m increases, the magnitude of each expression reduces rapidly, dependent on m to the squared pi, e to the minus m to the squared pi. Now, if we consider the possibilities when adding the expressions for m equals 1, 2 and 3, etc. Firstly, if we add m equals 1, m equals 2, the results will depend on the relative magnitudes of the two expressions. Given the m equals 1 expression is fixed, if the magnitude of the m equals 2 expression is relatively large, the combined expression will have an additional 0 as the expression turns positive and then will remain positive. This means that the expression would have no more zeros and no additional zeros as the m equals 3, 4, etc. expressions are added, since they're all positive. If the m equals 2 expression is relatively small, then the combined expression will not have any more zeros, as it will remain negative, it will remain below 0. If the magnitude of the expression is within a certain range, then there will be an even number of zeros as the expression turns positive, and then potentially negative and positive again, depending on the exact shape of the curves. And finally negative again, meaning after that it's possible for more zeros to be generated when the m equals 3 expression is added. This argument holds as for the expression as each value of m is added. Now the key implication here is that if adding any of the expressions either generates an odd number of new zeros or no new zeros, then there will be no new zeros generated for expressions with greater values of m, i.e. the real zeros will stop above a certain value of a. This is in fact what we observe in the following figures, highlighting m equals 1, m equals 1 plus m equals 2, m equals 1, m equals 2 and m equals 3, and m equals 1, 2, 3 and 4, as well as the negative versions of m equals 2, m equals 3 and m equals 4 curves for illustration of the relative magnitudes and interaction with the main curve. So you can see here for the two expressions, again, but this is looking at b equals naught, you can see at a big scale you can't see a huge amount. If you go into a bit more detail, then you can see that m equals 1 comes down, comes up again, and if you add the m equals 2, if you don't have the m equals 2, it stays negative. If you do add the m equals 2, it goes positive and negative and positive. Similarly, here you can see in a bit more detail that once you've added the m equals 2, then you have many zeros and then back to positive. Adding the m equals 3 means that it goes from negative here to back, getting more zeros as it keeps on crossing the line. So you need to keep on adding the m equals 3, etc. components to keep having zeros in the function. Looking again in more detail now at when b does not equal 0, firstly looking at the expression 5, so continued fraction, then minus an eighth minus b over 2 plus a over 2i. But b does not equal 0, and for the sake of this discussion we'll say it's positive. Having said that, if you have b negative, you're just switching around expressions 5 and 6. And looking at the expressions for each value of m individually, the magnitude of the continued fraction component will reduce, but the magnitude of the linear component here will increase, and it will actually increase by a larger value because it's linear compared with a continued fraction component, which is a very much reduced magnitude from the upper incomplete gamma function component. Similarly, for expression 6, you have the same issue. As b increases, the magnitude of the continued fraction component will increase, but the magnitude of the linear component will decrease, but by a larger value. The relative sizes of the magnitudes of the various components mean that for each value of m, the sum of expression 5 and 6, or the Riemann z function, for each value of a will have a greater magnitude, both for the complete function and for the real and imaginary components separately, when b does not equal 0 than when b does equal 0, which is different from looking at purely the sums of the incomplete gamma functions. If you remember there, then if you added the two components, they would be smaller than the sum when b equals 0. In this case, the sum will be bigger than when b equals 0. Very important. We'll see why that's important in a moment. The implication of this is that when summing the m equals 1, 2, 3 components, as b increases, the magnitude of the real curve increases. Similarly, the magnitude of the imaginary curve, when it's not identically 0, increases. This in turn means that for the combined function, as b increases, any part of the curves, real or imaginary, that are positive stay positive but also increase in magnitude. And similarly, any parts that are negative remain negative and increase in magnitude, which basically means that the curve continues. There are no additional zeros generated. The curve gets further away from 0 rather than getting close to 0 as the magnitude of b increases. Very important. No additional zeros are generated from the b equals 0 curve for the b does not equal 0 curves. Very importantly, this is what we observe in those graphs that we looked at earlier. If you can see here, you've got, oh well, we'll go back to this one. We can see here for the b equals 0 curve, which is the red one there. You can see the size of it there. For the b equals 0.5, it's a bigger magnitude and negative. Looking at that in a bit more detail, you can see here also the same thing for positive values. The black one, which is the b equal 5.5, is of a greater magnitude than the red one, which is a b equals 0 one. That continues all through. You can see it more clearly here. B equals 0.5, B equals 0.25, B equals 0. The magnitudes, whether positive or negative, increase, which means there can be no additional zeros generated. Very important. The results of these hold for any value of B, but you can't necessarily use the same arguments that we've used to show that it's right in the first place. Now, the second section, integration resulting in a power series. Start with the same equation which you saw before. The route to get to a power series is well known, so we take the results from Edwards, where you end up with this relatively simple looking one. The z of s equals sigma for n equals 0 to infinity of a to the 2n x to the I minus y to the 2n. Now, it's been proved that all the coefficients are positive, which means that if x equals 0, there can be no zeros, and if y equals 0, there are potentially many real zeros, depending on what the actual values are of a2n. It has been proven by Hadamard that z of s in this format does converge, that the coefficients do decrease rapidly. This was shown by Hadamard. It was necessary in the convergence of the product representation. Now, looking at another definition of the z function, also from Edwards, factorial function of s over 2 times s minus 1 times pi to the minus s over 2 times Riemann zeta of s. If we look at those individual components, we've seen the factorial function earlier, so that we know that it's a decreasing in magnitude, oscillatory about 0 function. The s minus 1 linear term, magnitude decreases slowly. Pi to the s minus s over 2, constant magnitude, oscillatory components, fixed magnitude of oscillation, and the zeta function. We look at that. We can see an illustration of that here, also oscillatory and slowly increasing, but very importantly, it's not increasing rapidly, which means that if you look at the product of the individual terms, the curve is oscillatory with decreasing magnitude of oscillation as r increases. If we look at when b equals 0, no imaginary element of the function, and the function tends to 0 in the limit, as expected. What this means is that for any value of r, there will be real zeros greater than that value of r, which means that there are real zeros all the way through the function. Now, the next thing that we do, another substitution. Instead of ai minus b to the 2n, or xi minus y to the 2n, can be written as r to the 2n cos theta plus I sine theta, de Moivre's theorem. And you can expand that as r to the 2n cos 2n theta plus I r to the 2n sine 2n theta, taking r to range from 0 to infinity and theta to range from pi by 2 to pi for our most relevant quadrant, which matches the xi minus y. The structure means that the pi to 2 pi half is a reflection of the 0 to pi half. We'll be focusing on the behavioural expression for r greater than 1. We don't need to worry about r less than or equal to 1. Now, taking that as a complete expression, z of s equals sigma n equals 0 to infinity of a2n r to the 2n cos theta plus I sine theta to the 2n. Just for illustration's sake, we've got some illustrations of the zeta function shown in the power series representation, which, as you would expect, is is the same shape as we've seen earlier from the gamma series representation. Just a confirmation that we're talking about the same function. Expanding the series that we have here, it looks like this series: a0 plus a2 r squared cos 2 theta, etc., plus I a2 r squared sine 2 theta, etc. Looking at those in more detail, real and imaginary parts of the expression are single valued for each r theta combination. Real and imaginary parts have a period of pi. For theta equals pi over 2, the expression is equal. Theta equals pi over 2, which is the same as saying that there is no real component. It's the same as the z function sigma n equals 0 to infinity of a2n ai to the 2n. We do see that for actual values of a2n, the expression does have multiple real zeros. We've seen that here. Similarly, for illustration, this is a graph of that function with varying theta equivalent to varying b, and as you can see, the graphs are very familiar. They're what we've seen in the incomplete gamma function series with varying b. Now, the reason why we're doing this is looking at the paths of the zeros. Firstly, looking at the real part zeros and using a substitution for theta equals pi over 2 plus epsilon, where epsilon is arbitrary. Doing that substitution and working through it, then we end up with the expression cos 2 theta equals minus cos 2 theta, cos 2 pi plus 2 plus epsilon, cos pi cos 2 epsilon minus sine pi sine 2 epsilon, which is minus cos 2 epsilon, and similarly cos 2 pi over 2 minus epsilon equals minus cos 2 epsilon. You can work through for all the cos 2n theta for all values of n with similar results. It's alternating signs, and what the implication of that is, the path of that function, which is reflected across theta equals pi over 2 for varying r. So you've got a family of curves non-intersecting and potentially passing through the theta equals pi by 2 line. When theta does not equal pi by 2, then we know the function extends from the zeros on the theta equals pi by 2 line. If the function does not pass through theta equals pi by 2, then it will have two reflected branches on either side of the theta equals pi by 2. But most importantly, non-intersecting with any of the other of the family of functions. You can go through the same arguments with the sine 2 theta or sine 2n theta to give the same results. Family of curves, non-intersecting, whether it passes through theta equals pi by 2 or not. So what we see here is a graph of both the real and imaginary zeros of the functions. You can see here the real and imaginary do alternate. These are for the actual values of a2n. And you can see non-intersection. You can also see that in this case it does not appear that the real and the imaginary ones intersect, except where the imaginary is identically 0. So that's an indication, but by no means rigorous. Now, taking that a stage further, looking at real plus imaginary and real minus imaginary part zeros. The complete function will be 0 when both real and imaginary expressions are equal to each other and both 0. Combining those, then we'll be looking at, say, equation 1, or expression 1, expression 2, a0 plus a2r squared cos 2 theta, etc., and a2r squared sine 2 theta, etc., equals 0. Combining 1 plus 2 and 1 minus 2 and placing them to be simultaneously 0, then we end up with the expression that is expressions 1 plus 2 and 1 minus 2 are reflected through pi, theta equals pi by 2, and if they cross theta equals pi by 2, there will be a coincident pair of real zeros on theta equals pi by 2. If they don't, then you'll have a reflected pair of imaginary zeros tracing reflected paths. Importantly, the functions are single valued for each r theta combination, and there are no intersections with any other of the same family of functions. So if you've got a pair of zeros, they're generated, say you've got zeros on the theta equals pi by 2 line, there will be no other zeros generated by intersections from other imaginary zeros. We can see here in this graph, again, there are no intersections with other zeros. So if you've got a pair of zeros on the line, then there will be, those are the only zeros you'll get. You won't generate any other zeros at a later stage for a different value of r generated by other curves from the same family. Very important. Once you've got some zeros, you won't get any more zeros. Combining all of these together in the conclusions, we knew previously theta of s does not have zeros outside the critical strip or critical area. So with b out bigger than a half, or plus a half I or minus a half I. In section 1 we showed that the z function with no imaginary component would either have all real zeros or all real zeros for a less than a certain value. Section 1, it was also shown that no additional real zeros from the case where b equals 0 can be generated when b does not equal 0 or is greater than 0. In section 2.1 it was shown that zeta of s with no imaginary component has real zeros greater than any fixed value of a, i.e. there are real zeros all the way through, which means that if you combine that with section 1, zeta of s with no imaginary component will have all real zeros. In addition, and in section 2.2, you can't generate, we were shown you can't generate any additional zeros due to the coincidence of imaginary zeros from the real and imaginary parts of zeta s. Combining all of those conclusions, we can say that all the roots of the Riemann z function, where s equals a half plus ti, no imaginary component, are real. Thank you very much.